Okay, y'all. So let's get the show on the road today. We have a couple things. We're going to spend a little bit of time on the Java collection classes. Not a huge amount because I don't think they're all that different from the C++ standard template library. So as always, I'll be focusing on differences between the two rather than the similarities. And then I want to spend most of my time on problem 2 of homework 2. And the reason I'll be doing that is it may be until you get to the concurrency at the end of the semester, the toughest problem that you'll have to do on the homework assignment. So I think based on the experience I had from the last time I taught the course, it's a good idea to spend a fair amount of time talking about how to do it. The reason it's doing a recursive search of a space to try to find the solution to a game. For those of you who took CS 140 from me or Dr. Plank, you know that he had a game where you wrote a lab to try to find the solution to it. And this is something similar, and then it also incorporates graphs from 302. And the reason we did this is because we were finding that we weren't really reviewing stuff that was being taught in 140 and 302. And it was decided 365 was a good place to make sure that we hit back on some of the concepts. So I'll talk more about it when I get there. I'm hoping to spend about 25 to 30 minutes on the collection classes and then about 45 to 50 minutes on that problem on homework 2. Okay, so the book did a good job of going over the basic classes in the Java collection classes. I just want to go over a couple things you need to know. First of all, technically maps are not part of the collection library. So even though they are generically linked in and you can think of them as a collection, they technically are not part of the collections library. You need to know that for the quiz today, okay? But if you want to get a collection from a map, then there's 3 different commands. I think it's called values. Great. I think it's keys. The last one I'm almost certainly going to get wrong, so let me look it up. So, pardon? No, I want where you get key value pairs. It's like entry set, but it's not, thanks, but let's see. There, it is called entry set. I wasn't going crazy. So and make sure that keys was right. Key set is what I needed, okay. So actually, it's not keys, it is key set. And then entry set. So values returns a collection of values. And of course, they're not necessarily ordered. If it's a ordered map, then the values are ordered. But if it's a hash map, values are in the order that they're stored in the hash table, so they're unordered. This will give you a set of keys, but sets are part of the collections. So while maps aren't, sets are part of the collections. They support the collections interface. And entry set will return key value pairs. A set. And again, a set is part of the collection. So why do I make the distinction? The reason is if you are part of the collections library, there's a standard set of methods, the so-called collections interface, that is implemented. Maps don't actually implement the complete collections interface. That's why they are not considered part of the collections library. So if you want to be able to treat a set of objects that are in a map as a collection, you have to use one of these three commands to extract them as a collection and then be able to operate on them as a collection. Okay? So that's a subtle but still important point. Questions about that? Okay. Second thing, the Java developers did not believe in operator overloading. Okay, why is that important? It's important for two reasons. First of all, maps and array lists don't support maps and array lists do not support the bracket notation. So in the standard template library, if you had a map of something in the STL, so this is the STL, and it was say map int string, say people, you could say something like people 10 equals Brad. You can't do that in Java. That's illegal in Java because the Java developers did not believe in operator overloading. So they give you commands for getting at that. So for an array list, you have to use the for array lists, you use .get and the index. And if you want to add something, you say .add and then the value. And let me check this because I didn't check before class, but I'm pretty sure I'm going to find that if you want to put something, it's going to be a put. I would be wrong. Set maybe? I always add to the end of the array list. Yep, it is set. Okay. So if you want to set something, it's an index and a value. Okay, and if you're using maps, you want to get something, it's get and the key. And if you want to put something in it, it's put the key and the value. And unlike in C++, where get, if it fails, returns an iterator, the get here returns null. So returns null if the key is not in the map. So there's no exception. It simply returns null. Now, of course, that means if null is a valid value, you don't know whether the key is in the map or whether it's simply the value, the key was in the map and the value was null. But there's way to check, you can look it up. There's also ways to check if the key exists. Okay, so there's another command. But at any rate, you can't use the overloads like you did. Okay, so that's the first thing. The second consequence of no operator overloading is iterators. So in the standard template library, you could do things like you could say for say A equals foo.iter or something like that. Okay, and then it'd be someone help me out here. What is, for an iterator in the C++ STL library, how do you check to see if you're at the end? End. Yep, it's foo.end. But then you could say, to advance it, you would say A++. And to get something from the iterator, you might say simply cout star A. Okay? You can't do that. The star A and the plus plus operators won't work. Okay? So in Java, you explicitly have to get an iterator and deal with the iterator interface. Again, the easiest thing to do is to just look it up. So you have the iterator interface, and you'll see that it has next. So that's what allows you to determine whether you proceed or not. Next returns the next element. So this is like, this one is comparable to end in C++. This one is comparable to the star operator in C++. Okay? So those are the basic ones, and then you can also remove items from a collection, although it's an optional operator. You'll get an exception if it's not supported. Okay? And every element in the collections library supports it. So if you have the collections API, okay, then there should be a way to get an iterator. Maybe not. Okay, let's go for array list. There we go. Come on. There we go. So generally collections have an iterator method that returns an iterator with a specific type. Okay, and then you simply iterate through the elements using has, next, and next. You'll notice that scanner essentially implements the iterator interface because it has the has, next, and next methods. So scanner effectively is implementing the iterator interface. Okay, so you'll essentially have to use explicit iterators like this in order to iterate through collections. Okay, questions about that? Okay, so you'll need to use iterators. Third difference, important difference between Java and C++ is that Java collection classes cannot store primitive types. That means my Outlook is open. So even when you mute your computer, your Macintosh, Outlook seemingly decides, hey, I'm so important, I can interrupt whatever you're doing with a beep. So that's what happens. Okay. So Java collection classes cannot store primitive types. That's kind of annoying. Okay, it's an artifact of their original design, which is that they had an object at the top of the inheritance hierarchy. And then they designed their collection classes around this idea. So for example, if they had a list, the idea was you could store anything in a list by simply creating a list of objects. The issue is that that required anything you store on a list to be an instance of some class. And therefore, it excluded primitive types. Now, they later went to using templates, but the underlying mechanism that they use for implementing templates is their old idea of everything can be cast into an object, and primitive types cannot be cast into an object. So it turns out that even with templates, you're not allowed to specify primitive types. Just a second. There is a workaround, so if you're going to ask about that, okay. What?
You probably already said it, but what's a collection class?
A collection class is similar to one of the classes in the STO in C++. So Java calls it the collection classes, C++ calls it the standard template library. Okay, so standard template library, collection classes. Okay, so you can't store primitive types. That's a huge drawback because generally keys are things like numbers. Okay, so Java does have the notion of wrapper types. And that was the last thing in my lecture notes from Tuesday, was that the wrapper classes. So this is actually at the bottom of the notes from Tuesday, because the type wrappers also can be used to convert numeric strings. Okay, and I thought I had silenced that, but apparently not. Do you want to know how to become very popular? Incredibly popular. It would be buy a car. Yes, Brad is in the market for a car. Brad went to TrueCar.com to try to look at inventory for a few cars. And since then, Brad has had no shortage of friends. Every day, tons and tons of callers. And I thought I had put on Do Not Disturb, but I did not. Not one of them has been answered yet because I was not looking to actually go to a dealership. I just wanted to look at my options, but I'm everyone's best friend now. Okay, so getting back to what we were talking about. So we have wrapper objects, and we have one for each of the primitive types. And essentially, if you know the name of the primitive type, you know the name of the wrapper class, with the obvious exception of which there's a couple here that are not the same. There's two. Devin.
Boolean and character?
Nope, Boolean is actually spelled out in Java. You got character. Integer. So integer and character. So primitive type for an integer is int. Primitive type for a character is char. The other ones exactly mimic what the primitive type is. So you can store, if you need to store a primitive type into a collection object, you wrap it in one of these classes. And Java realized it was such a pain in the neck to always create new classes and then cast down. You have to then, if you want to use a primitive type, cast it down, that they have automatic unwrapping and unwrapping operations. So if you declare something as map integer, say Boolean, okay, foo, and later you're allowed to say foo.put, say 10 and true, and Java will automatically box. It's called boxing. Java automatically boxes wraps these types. Okay, so it will automatically create an integer object to hold the 10 and a Boolean object to hold the bool. And you will be able to say things like int, well, yeah, you can say things like int x, or actually Boolean, x equals foo dot get 10, and it will automatically box the 10 for purposes of performing the search, and it will automatically unbox the Boolean and put it into the Boolean type. So Java behind the scenes is putting in operations that will automatically create a new object to wrap your primitive types and automatically unwrap them for you. Okay, you can't, I'm not sure that you could put it into an add statement. I've not tried that. So if you tried if you had like an integer, so let's say this was instead of Boolean integer, and you tried to do something like foo.get 10 plus foo.get 20, I'm not sure if that would work or not, I'll be honest. Haven't ever tried it. Seems like it should, but I'm not positive on that one. Okay? At any rate, what you need to know is that you can, through these wrappers, that's how you store primitive types into the collection objects. Okay? And that's also how you can convert strings to numbers. So each one of these has a parse command and then the name of the type. So in this case, parse double. And if you give it a string, it will try to convert the string to a value of whatever type you're parsing. If it fails, you get a number format exception for numbers. For Booleans, it turns out that the parse Boolean will return false unless the string is some variation of true. So any combination of upper and lowercase letters making up true will cause the parse Boolean to return true. Otherwise, it returns false, which is different than a scanner. A scanner, when you try to say next Boolean, the string literally has to be either some form of true or some form of false, or else you get an input mismatch exception. So I find this annoying because it's inconsistent. Okay? So that's how in C++ you would use A to I or A to F. In C++, you might use string stream objects. In Java, if you want to convert strings to numbers, you use the wrapper classes. Okay? And conversely, if you need to convert something to a string, you use the strings value of method. And that is overloaded so that whatever type of primitive type you give it, it will convert it to the appropriate string. So if you need to convert a primitive type to a string class provides a value of object. Okay? Questions? Okay, getting near the end of the things I need to say. What else? The collections classes are in java.util. So you get them from the java.util. That's where they come from. Okay, so I'll just say where they come from, where collections are housed. So that's also where the scanner class was located. You'll notice that there is this kind of unusual thing that keeps coming up, the word interface. Not going to spend a lot of time on it yet. We're going to get to it very shortly. An interface is different than a class. An interface is like an abstract type, or another way to think of it is like an API for Application Programmer Interface. It defines a type, but it doesn't define, so an interface defines a set of methods. So for example, the iterator interface, okay, it's an interface, and it defines a set of methods. But it doesn't implement the methods. It's an abstract type. You can have classes that implement these methods. So you would find, for example, that if you have a hash map, let's now find a hash map. You find that it implements, of course it doesn't implement an iterator because it's not in the collection class. There we go. Implements, should implement iterator. Well, yeah, you're right. That was, okay. Oh, it returns an iterator. Sorry, it returns an iterator. It supports it iterable, but that's different. So it also gives you the ability to go through it as an iterator, but that's different. It's actually not supporting an iterator. So what do I want? Let's go to list interface. Sorry, let's forget about the iterable interface and go to the list interface. Okay, so here's a list. And again, it's an interface. It supports various operations that you would expect from a linked list. So add, clear, contains, is empty. Now, an array list implements a list. Okay, there we go. It implements a list. So if you were to see its definition, you would say class array list implements. And what that's saying is it guarantees that it implements all of the methods in the list interface. Every single method that's in the list interface is implemented in the array list. So if I have something that I declare to be of type list, I can actually assign to it something of type array list. I can say equals new array list. Because array list supports all the methods in the list interface. So even though list is not a class itself, it's an interface, you can declare a variable of that type. And then you can assign to that variable any object that supports that type's interface. So an array list supports the interface for a list, therefore I can assign to it. So in the collections library, you actually have a set of interfaces which the book went through. So when you look today at the book, it went through the major methods or interfaces. So list, map, set, queue, dequeue are the major interfaces. And then some of the implementing linked list, hash map, hash set, they're classes that implement that interface. But there's other classes that implement it too. For example, for a list, array list implements the list interface. Yes?
Why does the book list it under collections?
Because generically, people think of maps as part of collections. It's just that it's a technical detail that they don't implement the collection interface. So if I have a type variable declared as collections, I can't assign a map object to it because a map does not support that. Whereas list, set, queue, and dequeue all could be assigned to. So people just lump maps in with collections. It's just there's this slight technical detail that you can't assign a map object directly to a collections type.
And then the technical detail is that you can't iterate through a map.
Correct. If you want to iterate through a map, you convert it to a collection object using one of those three methods I showed you earlier, extract an iterator, and then you iterate. Okay. Okay. So these are the different interfaces, and then you have implementations of them. So for example, a queue, one thing it supports, there's a priority queue class that you can use, and it will implement a priority queue. For your homework 2, you'll need to use a stack, and it actually extends a vector, and I forget what a vector extends. One thing that is confusing, there are two things that appear to implement extendable arrays, array lists and vectors. In C++, you use a vector. In Java, you should use an array list for a single-threaded app, which is what you are using. You use vectors when you are dealing with multi-threaded apps. So for the assignments early on in this class, use array lists. Vectors are heavier weight because they have synchronization protocols that prevent race conditions. Array lists are lighter weight because they don't have synchronization protocols. Use array lists, don't use vectors. It won't change the correctness of your program, but it will change the efficiency of your program. So use array lists. Questions about that? Okay. I know I'm moving fast. If I move too fast, this is also in the video lecture that's posted. There is, by the way, okay, so final thing for collections is there are various sorting algorithms. So you can sort, in fact, I believe it is collections.sort. And if you give it a collection, it will sort it in the natural order. Okay? It assumes that this collection has a .compared_to method. Remember that from strings? Returns negative number if A is less than B. So something less than 0. If A is equal to B, it returns 0. If A is greater than B, returns something greater than 0. So it assumes it has a compare_to method available. That is not an object. Yes, Devin?
Is compare to internally just subtraction from
So that's a cute trick, but it's not always. You can use it for numbers. So I was going to show that cute trick. So compare_to is not in an object. Equals is. So for object, equals is defined, but compare_to is not. So if you want to be able to sort something, you can do it in one of two ways. First way is that this collection object will implement something called the comparable interface. And it has one method, which is public int compare_to. So one way you can do it, and it takes one argument, which is a value of the particular type. If you forget to do public, and I do all the time, you get a very unhappy compiler that says something about how the, well, here, let me show you because it will happen to you, because it happens to me all the time. So, you generally have to give the type of the thing you're comparing. Okay, now I will say int compare to foo. And I'm just going to return 0 for the time being. Notice I've forgotten to put public in front of it, right? There's no public there, correct? Well, first of all, I might try to put an argument there. Okay, and it comes up with attempting to assign weaker access privileges was private where T is a type variable. T extends object declared in interface. And you're thinking, wow, I must have done something wrong maybe with this foo or something. No, what you forgot to do was put a public in front of that int. Okay, so when you see this very opaque error message when you're implementing an interface, it's because you forgot to put public in front of your method declaration. Okay, so that's one way. And then Devin had that cute trick, which is when you are comparing two numbers, just subtract them. Okay, so just if you're comparing two numbers, just return whatever you are. Let's say it's you're comparing ages, return age minus v dot age. Okay, that automatically works for any number. It's a cute trick. So remember it for numbers. It works for all types of numbers. Okay, there's a second way. Let's say you don't want to support the compared to the comparable interface, or you want to sort in something other than the natural order. Maybe you want to sort in reverse order rather than ascending order, so descending order. So a second thing you can do, so that was the comparable interface. The second thing you can do is pass to collections.sort something called a comparator. It's a comparator interface. So, Java does not support function pointers. You can't declare a function and pass a function pointer to something like you can in C++ or C. What you have to do is wrap your function in an object. Then you pass that object to the function, and that function will have an agreed upon name. So, interface comparator type E. Now you fill that in with whatever type. It's not, the reason I have E there is that's the generic way Java shows where you fill in the specific type. Okay? And it is int public compare. And it takes two objects of type E. So the agreed upon method that sort wants is a method named compare that takes two objects of type E and returns an int. And it's the same thing. Less than 0, this is V1 and V2. If it's less than 0, V1 is less than V2. If it's equal to 0, V1 is equal to V2. If it's greater than 0, V1 is greater than V2. You will often see people do this. When they call .sort, you will often see them give the collection, and then they will create the comparator right then and there. You will see them say new comparator. Let's say I was comparing two employees. Right then and there, you will see int compare. Notice I already forgot to put the public, because I always do. It's one of my great joys of life. Okay, and I'll just have them return e1.age minus e2.age. So I'm comparing on their age. See, that one matches that one. This one matches that one. We are good. And then this matches this one right here. So this creates an anonymous class. Java actually creates a source file that creates an instance of a class that implements the comparator interface. And if this particular sort method was embedded in a class called foo, then when you compiled foo, you would see foo $1.class. And this would be the compiled implementation of this anonymous class. So Java automatically creates an anonymous class, compiles it, and names it $1 or foo $1, foo $2, foo $3, and so on. You'll never see what the .java implementation looks like. The compiler automatically creates a file, compiles it, and outputs the .class file. Okay? So these are called anonymous classes. Okay? It's creating an anonymous class that implements this particular interface. You just got to get used to it. It's kind of clunky, but it goes back to the fact that Java doesn't support function pointers. So you can't pass a function directly in as a argument. If you want to pass a function in as an argument, you wrap it in a class. Okay? So again, two ways for sorting a collection. One is simply have your collection implement the comparable interface. So that allows you to compare two objects, like string implements the compare to interface. Or if you don't want to implement a compare to method, or you want to sort in some other order, then pass in a comparator object, and it must support the comparator interface. We good? Okay, deep breath. I know I went somewhat fast. I covered a few things the book didn't, so let's just quickly also review that. Okay, so maps are not strictly part of the collections library. So if you want to get a collection from them, you use one of these three methods. The second thing the book did not mention is that the Java developers did not believe in operator overloading. So you have to use different methods for maps and array lists. You can't use the square brackets, nor for iterators can you use the plus plus and the star. Instead, you have to get an instance of the iterator class, and it will use has next and next. Okay, then Java collection classes cannot store primitive types. You wrap them in wrapper classes. Java will automatically box and unbox these primitive types for you. You find the collection objects in the java.util library, and the collections library actually defines a set of interfaces, then it defines a set of classes that implement these interfaces. You typically are using the classes. And finally, the sort method, pretty handy. Okay? Final thing, actually one final thing, because you'll need it for the homework assignment. You sometimes want to be able to sort arrays. Okay? Arrays aren't part of the collection library, but there is import. Actually, I guess it is part of, might technically be considered part of the. You can import an object called java.util.arrays. And then you can say arrays.sort. And you can pass it either an array or an array and a comparator. So you can sort arrays of primitive types. So arrays.sort will sort arrays. Yes.
You said the .next was comparable to the,
Plus to the star.
but if I call .next multiple times, it'll dereference.
It will advance the iterator. So it's not quite comparable to the star. Next actually gives you the next token and advances the iterator. So yes, thank you. Next is a little different than star because not only does it return the next item in your collection, it advances the iterator. So you don't need to do the plus plus. It's like star, it's like next combined star and plus plus. Okay, thanks. Did y'all get that? That for an iterator, going back to an iterator, whoops, not that one. Not that one. Iterators. Next. The next method actually combines the functionality of C++'s star and plus plus operators because it retrieves the value of the next item in the collection and it advances the iterator. So if you're writing a loop that goes through an iterator, it actually looks a little different. It might be for, say, a equals foo.iterator, a dot has next, and then that's it. You don't have the third item because next, like let's say you say system.out.println, a dot next, not only will that print that the current item pointed to by A, it will also advance A to the next item in the collection. Okay, so right here, there's nothing.
But
yes.
The item, the value returned is before it traverses borders?
No. It's when you get the iterator, it is just like in C++. A initially points to the first item in the collection. When you call, yes, so when you call .next, you get whatever A points to.
Okay.
And then it advances A.
Yeah, okay.
Okay, if you prefer to think of it, think of A as between, then next returns this item, and then advances A to here. But really what's happening is A points here. When you say next, it gives you whatever A points to, and advances A to the next item in the collection. So when you get the iterator, A is set up to point to the first item in the collection. Okay? I know that's confusing, but it is what it is. Okay? Okay, homework problem 2. Brad enjoys a website called lumosity.com. It has all kinds of brain games on it. Yes, we're starting it with a story. It has a game called Pet Detective. And in Pet Detective, I love it. So someone else, am I playing this? I must be playing it. Wow. Okay, I like the sound effects. Okay, let's just turn it down. Okay. Okay, now that's irritating. It's saying, overridden, denied. That's amazing. Gosh. Okay, try to fight through this noise because I don't know how to actually stop it now.
You can click the speaker on the tab for Firefox.
Okay, thank
Top
you.
right.
Top. Thank you. Goodness gracious. Okay. Sounds good for like 5 seconds. Okay, so you have a bunch of pets, and your goal is to return the pets, to take the pets, and take them to their homes. Okay. Now, it's not quite that simple. You have gas, and the goal of the game is to, oh, come on, that was supposed to just, oops. The goal of the game is you get 24 moves. You have to deliver all the pets to the homes in 24 moves. Okay? There's another wrinkle. You can only have 4 pets in the car at one time. See, here's the car. It's now full. So I'm not allowed, if I try to click on the fox, it won't let me. It says full car. So before I can pick up another pet, I need to drop one off. Okay? Then I can either go to another home or I can get another pet. The idea is to finish in 24 moves. Just like Dr. Planck sometimes gets frustrated, at the highest level of this game, it can get pretty gnarly. And it turns out Lumosity sometimes apparently puts in unsolvable puzzles, which I discovered only after I wrote a program because I was so frustrated with one of them that I wrote a program to solve it and found out it wasn't solvable. Lumosity was off by 1 and the best you could do was 37. Okay, so homework 2 is about you writing a program that solves one of these puzzles. Okay, so you have pets, you have pet homes, and you have the constraint that you can only put 4 pets in a car at once. So your input file looks like this, an empty file. Now, so the first line of input is the number of units you're allowed to move the car. So in this case, I have to move, I'm limited to 17 moves, 17 spaces that I can move. So from the car to the turtle, then it gives you all the distances between adjacent things. So from the car to the turtle is 1 unit, from the car to the cardinal home is 1 unit, from the car to the fox is 1, from the blue dog home to the yellow dog home is 1. So if you look back here, what I do is give you an input file where, so for example, this, I call this a marmot. The marmot is 2 from the rabbit, 1, 2. It is 1 from the blue dog home. So I give you all the directly adjacent edges. So you won't get something for marmot to yellow dog because there's an intervening object. Here, for car, you would get the distance from the car to the marmot and the car to, marmot home and the car to the iguana home. Okay, but you won't get anything else because the car has only 2 ways it can go, so it will run into those 2 obstacles first. Just 1 second, okay, then I'll let you. So the first line guaranteed to be the number of units the car is allowed to travel. The next lines are guaranteed to be the ones for the car, with the car first. After that, the input can be in any order. Okay, but it's guaranteed that all the car edges are first. Okay, because you'll see that we're going to represent this as a graph. You want your car to be vertex 0. Yes.
Is there a way to tell whether it's horizontal or vertical?
It doesn't matter. Yep, don't worry about, there is. It doesn't matter. Okay, so in the solution, whether it's a horizontal move or it doesn't matter. Okay, it's just a move. And a move means, so if I move the car to this turtle, it's going to cost me 2. Okay? And if I want to move to the iguana, it's going to cost me 3. So you're going to see this go from 34 out of 36. It goes to 31 because I've used up 3 of my moves. But it doesn't matter whether it's horizontal or here. I had to actually go left and then up. Doesn't matter. It's just 3. So you can represent this as a graph. So we want to give you practice with graphs. So what you need to do is create a vertex for each pet and for each house. Okay? And the way I guarantee it is if you have, I call this a cat, this object right here, a cat, its home has the underscore home. That's guaranteed in my input. So every pet has an underscore home suffix, which is its home. So if you have n pets, you'll have 2n plus 1 vertices, because the car is one of the vertices. Okay? So you want to move the car. So the idea is you want to move the car essentially to each vertex once, delivering all the pets to their homes. This is an NP-complete problem. It's a Hamiltonian cycle, if you heard about Hamiltonian cycles in 302. If you didn't, don't worry about it. But it is NP-complete. So it can take a fair amount of time. You have to use a so-called exhaustive search strategy. So what you're going to do, you're going to read in these lines. I don't tell you in advance how many pets there are. Why is that? I want to force you to use an array list. If I told you how many pets there were, you could go straight ahead and create an array. But I want to give you practice using the collection classes. So my suggestion, there's not that many lines of input. Read each line of input into an array list object. And as you do so, keep track of how many pets you see. And just count them up. Okay, actually, you'll also see these. So count up actually the number of vertices you see. So just count it up as you go along. Put them into a map. Keyed on string. Okay, so every time you see one of these things, you put it into a hash map. Check to see whether it already exists. If it doesn't, you add 1 to your number of vertices. It's pretty simple, at least for setting up the graph. Okay, now, this isn't what got people last time. What got people is how to perform the search. Okay, and the second problem, which isn't, so first of all, you're only given the distances between adjacent vertices. You actually, in order to solve this problem, you need to know the minimum distance between every pair of vertices. Okay? Because, like in, let me reset, I can't go directly to a house. I can't go to a home if I don't have that pet in the car. I can only go to a home if I have the pet in the car. So my first move here can't be to either of my adjacent vertices. It has to be to a pet, like the turtle. So I actually have to create an adjacency matrix that contains the minimum distance between each pair of vertices. That's called the Floyd-Warshall algorithm. I'll get to that momentarily. Let's just say we know we have this adjacency vertex. Now you're back to a problem that you had in 140. Whoops, I know that both Dr. Planck and Dr. Greger goes over Sudoku with you, how to solve Sudoku. You solve Sudoku just like you solve this problem. It is a recursive backtracing problem. Effectively, what you have is a large tree. Okay, so you have your car. At step 1, you have a whole bunch of options. You can go to pet 1 or pet 2, all the way up to pet n. Those are your options. If you go to pet 1, the next step you have the option of going to pet 1's home, or you have the option of going to pet 2, or to any of the pet n's. Okay, let's say you go to pet 1 home. You now have the option of going to pet 2, pet 3, all the way up to pet n. Let's say instead you go, after you pick up pet 1, you go to pet 2. Now you can go to pet 1 home, or you can go to pet 2 home, or you can go to any of the remaining pets. So you see it's a huge search tree. But you can't represent that search tree in memory because it's exponentially big. So what you have to do is, in essence, go down one branch of the tree at a time until you get to either the bottom of the tree and you've solved it, meaning if you had 36 units, you managed to deliver all the pets to their homes in 36 time units or less, actually 36 gas units or less. Or you get to some point where you've exceeded your quota. Let's say you pick up pet 2, and when you do that, you've exceeded your quota, in which case you backtrace to the previous node, and then you go down the next node of the tree. So all you're doing is effectively doing what kind of search? Do you all remember what the search is? Depth first search on the tree. Okay? It's just a depth first search on a tree. So you have to write a depth first search. Now, my suggestion to stop your program from running forever. It is probably not right to start by having my car go to a marmot. I just blew 7 units of gas. Okay? So you might want to be a little intelligent about your search. I suggest that for each vertex, you keep an ordered list of vertices in ascending order based on their distance from you. Okay, so if you're at the cat home, you just dropped off the cat, you're more likely to want to go to the blue dog, the armadillo, or the turtle home next. That may not be right. If it's not right, it is more likely that you would want to next go to the fox home, the cat, the yellow dog home. Uh-oh, 2 yellow dogs. I forget how I call these. What do I do in this case? Blue dog, yellow dog, fox. I'll figure it out. There's something. Maybe it's a brown dog. Who knows? I'll figure it out. At any rate, the idea is for each vertex, keep with it a set of vertices in sorted ascending order. Okay? So what you're going to do is you're going to run this Floyd-Warshall algorithm, which the last thing I'm going to talk about. So don't worry, I'll tell you. So you have your vertices. Convert them to numbers. My suggestion is you give them numeric values. So as you encounter each vertex, car should be 0. As you encounter each vertex, assign it an integer. So you can use integer indexes in arrays. It makes your life easier. Okay? So when you're done, you'll have distances. Like from the car, you might have 0 to the car, 2 to 1, 6 to 2, 3 to 3, 1 to 4. So for each of your vertices, I suggest you sort it now. So you'll need to keep pairs. You'll need to keep the 2 vertex, and you'll need to keep the distance. So you'll actually have to create a class called edge. And then you will do arrays dot sort on, in this case, let's say the name of the adjacency matrix is distances. You would sort distances 0. And you would give it a comparator object that could compare 2 edges based on what? Distance. And you would use what trick to compare them? Subtraction. So that's why I told you about arrays.sort, because you'll need to use it. At least my suggestion is unless you like to implement selection sort yourself. But you might as well use the Java sort method. It is so much simpler. Okay, last thing. I want to find the shortest distance between all of my vertices. And initially, I only am given a few distances. So initially, most of them seem to be infinity. I might have 1. This might be infinity, this might be infinity. I might know this is 2, and I might know, but this might be infinity. I might know the distance from 1 to 3 is 2, but this might be infinity. So what I need to do is fill that in so that I have the shortest distances between all of my vertices. There is an algorithm that does that. It's actually pretty simple, called the Floyd-Warshall algorithm. I have a pointer to it from the homework assignment. Okay? It is very simple, the idea. Okay? It's based on induction. Let's say that I have numbered my vertices, and thus far, I know the shortest distance from I to j that goes through all vertices numbered from 0 to k minus 1. So far, I have the shortest, I know the shortest path that goes from every pair of vertices, going only through the vertices from 0 to k minus 1. What I do at step k is I find the shortest path from all pairs of vertices that go through the vertices from 0 to k. So all I do is I say that my new shortest path is whatever the previous shortest path was from I to j. So my previous shortest path from I to j is this amount. Or there might be a shortest path that goes from I to k, and then from k to j through the k minus 1 vertices. So whichever of those two is the shortest is the one I now use. That's all I have to do. Okay? And I don't have time for the proof, but if you think about it, it makes sense that if you add vertex k, so you have some previously, I to j, there was some shortest path. Okay, now there might be some path from I to k and k to j. Okay, so you either choose this path or you choose that path. Okay, and you might say, okay, so this is 8, this is 3, this is 4. So clearly you should go through k. Well, that's it. I mean, you couldn't, through the k minus 1 vertices, you couldn't find any shorter path from I to j. Now you added k, so the shortest path from I to j that goes through k has to be this one. There can't be any other one that goes through k that's going to be shorter. Okay, you can think about it, but there's not. Okay, so the algorithm, very simple. Look at that, they give it to you. Okay, so initially, your distances to yourself is 0, and you're going to assign also anything you know. So you first assign all your distances to infinity. Now, notice they add infinity to infinity sometimes down here. Don't use max.infinity like I did last night and wonder why your program's not working. Because max.infinity plus max.infinity is arithmetic overflow. So define some other constant for infinity like 1,000. I guarantee that none of your paths will be longer than 1,000. Okay, so define a constant called infinity, make it something like 1,000. Something that won't cause arithmetic overflow. So you initialize everything to infinity, you go back and wherever you have an edge that I input for you, you fill in that. And then you also set every distance from a vertex to itself to 0. Then this is just saying from k from 1 to v. So that's k. Then you go through all pairs of vertices. Lines 7 and 8 are just going through all pairs of vertices. And then this is just that if statement you saw earlier that is just saying if the distance from I to k plus k to j is less than the current shortest distance, update the distance. We don't care, we don't need to know what path, how to get there, okay? Because Lumosity, generously, if going back to the game, Lumosity always chooses the shortest path. So you don't need to know which vertices comprise that shortest path. Lumosity figures it out for you, okay? So all we care about is the shortest path between each pair of vertices. The Floyd-Warshall algorithm gives it to you. It's really short. It is that short. I have pretty much line for line that in my code. Okay? So don't wait till the last minute to do it, but it does force you to go back and think about graphs from 302. It forces you to go back and think about recursive backtracking from 140. Okay? And remember, when you backtrack, you sometimes have to undo stuff. Okay, that's the last thing I'll leave you with, is that, oh, I think I undid it. But if it turns out, so let's say I go down a path, okay, this is the last thing. Let's say I go down a path, being at pet 2, I go and I deliver pet 2 to pet 2 home. That frees up a space in the car. If I have to backtrack to P2, I have to remember to add 1 back to the number of pets in the car because the pet's no longer delivered to pet 2 home. That's just like Sudoku, where if something doesn't work, you have to erase the value you put into that cell. So just remember, when you backtrace, you have to do a little bit of undoing. Okay? So good luck with homework 2. Feel free to post on Piazza over the weekend. I'll be looking at it. If you have trouble, I will post this video with a link because you may find you need to go to this video.
How does that, it's gonna be solvable, right? You said that yours could solve it.
No, I will give you 1 or 2 small things where it's not solvable.
So we should output that.
Yes, so I give you my executable, so it shows what output to generate, because we will do it using strip-based comparisons. Last thing, a couple of the puzzles may take a minute. Don't worry if it takes a little while, okay? Start with small puzzles and work up to the bigger ones, but there's one of mine that takes me 50 seconds, okay? If you do it stupidly and don't sort it, it could take hours. You're all free to go. Have a good weekend.